All right, this is the review of the momentum pretest. You have an 8-gram bullet that's shot into a 4 kilogram block. Probably should note that. This is kilograms, this is grams. The block's at rest on a frictionless horizontal surface. You can see it in the picture. Bullet remains lodged, so it's a sticky collision. Block that moves against a spring and compresses it by 8.9 centimeters. The force/spring constant K is that. What's the magnitude of the impulse on the block, including the bullet inside, due to the spring during the entire time interval during which the block compresses the spring? Nothing like getting started off on the right foot here. So first off, you can say that J is equal to F dot T, but we have no idea what's going on there. Or you could say J is equal to delta P. For this one to work, we have to know M delta V, which I think this is the way we want to go, because I know that the bullet has some initial velocity. When it hits the other block, whatever kinetic energy those two have together, it's going to be transferred into the potential energy of that spring. So I think if we work our way backwards, we can say KE equals PES. If we expand that out, it's 1/2 M. This is M combined, V combined squared equals 1/2 K x squared. If you plug in all the appropriate information here, 1400 newtons per meter, 8.9 centimeters is the compression. I would convert that to 0.89 meters. That'll make the math work and turn this into joules. I'm going to pause here and do a calculation. Alright, so this number is 5.545 joules. So that's how much energy the spring gained, also how much energy the block had. Now you can look at the impulse on the block due to the spring as M delta V. M is the combined mass, so it's 4 plus 0.008 kilograms times, and delta V, delta V is during which the block compresses the spring. V final there is 0. So 0 minus, and V initial we're going to get from this number here, if we set this equal to the 1/2 mv squared. So 1/2 4.008 kilograms times V combined squared equals that 5.545 joule number. V combined, again I'll pause this, V combined is 1.66 meters per second. So that's my initial velocity. I'm going to plug that in back up here, and I'm going to get 4.08 times negative 1.66, and I get negative 6.65 kilogram meter per second. Now they ask for the magnitude, so they don't care about the sign here, and it looks like B is the correct answer. All that negative means is the impulse was to act in the opposite direction of the block, which makes sense. It slowed the block down. Alright, next question. You have a mass baseball dropped from rest at a speed right before it hits the ground. It rebounds with an upward speed of that. The ball is in contact with the ground for that long. What's the average force exerted by the ground on the ball? So I'm going to use the change in momentum impulse theorem. J is delta P. You guys might remember it as F dot T equals M delta V. This is your F average that you're looking for. This T is 0.014 seconds. M is 0.140 kilograms, and delta V, V final, is upward. Let's say up is positive, so 1 meter per second, minus V initial was 1.2 downward, so minus a negative 1.2 meters per second, equals, if I solve for F, 0.14 times 2.2 divided by 0.014 is 22 newtons, and it's positive, which we said up was positive, so 22 newtons upwards. C is the right answer. All right, next question. Fire hose is turned on the door of a burning building in order to knock the door down. This requires a force of 1,000 newtons. If the hose delivers 40 kilograms of water per second, what is the minimum velocity of the stream needed to knock the door down, assuming the water doesn't bounce back? Again, we're going to use F equals m delta V. I should write over here times T. If I rearrange it, that T comes over here because we're solving for what the force is. This is a little weird in that the m per second is given here, which we really don't do that often, but it's going to work out. So it's 40 kilograms per second, just sort of dimensional analysis. 1,000 is the force, and you want to know what's the velocity. So if I work my way backwards, V is equal to 1,000 newtons divided by 40 kilograms per second, and that is 25 meters per second. Answer D. Next question. An egg falls from a bird's nest in a tree and feels no effect due to the air as it falls. So if there's no air resistance, no effects due to the air, the total mechanical energy will be conserved. So mechanical energy, that's a good one. We'll say yes to that. Momentum is always conserved, so P before always equals P after. Alright, it's at this point that I realize I just screwed up. This is not true. Actually, this is a good learning point. This is true as long as there's no outside force. And when we talk about collisions, for the most part, there is no outside force that's adding any extra momentum to it. But in this case, gravity kind of obviously is an outside force that's causing a change in momentum. The velocity is increasing of that egg, so mv is going up. So in this case, only its mechanical energy is conserved. It's Monday morning. A rubber ball and a lump of clay have equal mass. They are thrown with equal speed against the wall. The ball bounces back with nearly the same speed with which it hit. The clay sticks to the wall. Which of these objects experiences the greater momentum change? I'm going to guess the ball the first time through here. The reason why is the momentum change is m delta V. And if you think about it, m V final minus V initial. If they have equal mass, that doesn't matter. And if they have equal speed initially, that doesn't matter. What matters is what happens after, and the ball is going to bounce. So the greater change in V is going to come about because of the bounce.